Hello, welcome to this keynote titled Implication of Wear and Abnormal Events on the Reliability of Silicon Carbide MOSFETs for Automotive. First of all, let me seize the opportunity to thank the VPPC 2021 conference organization and in particular Professor Paolo Arbolea for inviting me to this keynote. My name is Francesco Iannuzzo. I'm a professor at Aalborg University Energy Department and I'm also a member of the Center of Reliable Power Electronics Corp in my university. This is the outline of my speech. After an introduction about power electronics and automotive scenarios and reliability of silicon carbide MOSFETs and what is demanded, I'll be introducing what in my perspective are current challenges in silicon carbide MOSFETs regarding packaging issues, semiconductor issues, short circuit issues. And after all, I will try drawing some prospects and summary. All right, let's start with the introduction, talking about power electronics and automotive scenarios and reliability of silicon carbide MOSFETs and what is demanded. What is power electronics used? Power electronics has become very quickly after, I would say, 20, 30, 40 years, I would say, extensive usage has been becoming, I would say, an enabling technology for transporting energy from the generation places through the transmission facilities all the way down to the utilization sites like cities, infrastructures, and industries and homes. Power electronics is present basically in every single transition of the energy from the very beginning to the very end because it is needed along the way to change all the parameters including voltage, current, frequency, and something like this. Among other applications where power electronics is becoming dominant, I would like to emphasize the importance which recently has been given to the automotive industry by power electronics. Thanks to power electronics, electric vehicles have been hybrid electric vehicles, all the categories of them have been made possible, and nowadays we can witness a booming process in this field. Yeah, sticking on the electric vehicle sector, there is an obvious global development in terms of market. For example, if you look at this picture from the International Energy Agency reported in 2018, there is I would say, educated forecast for getting 12 times as big the current number of vehicles, the electric vehicles all over the world. Most of them will be basically battery powered, which means that they are both weight and efficiency critical. And obviously, if you look at this chart here, obviously the PLDV, passenger light duty vehicles and light commercial vehicles will be dominating the scenario over the last 10 years, a lot more than buses and trucks. All right. According to another survey, I would say market forecast from Yodel in Europe, what is going to drive the power electronics development in the current decade is definitely automotive, more than renewables and more than industrial applications. So special attention should be paid to this sector. More specifically, what are the power electronic demands in automotive? Well, in automotive applications, basically, we look for higher frequency, which makes possible to use a smaller volume and weight and higher efficiency, higher temperature range with the various working conditions and less cooling demand, higher robustness in terms of longer lifetime, short circuit, and overcurrent capability. But this is a relatively complicated scenario because if we think of a typical electric vehicles, then we can find power electronic conversion, I would say full power electronic conversion, at least in two places, which is basically the battery converter and the engine, the motor drive converter. And I would say a significant percentage of full power, for example, for the battery charger side. So all these things require all this I would say requisites I've been listing here. So higher frequency, higher efficiency, higher temperature range, and so on. Question is, would silicon carbide be the answer to this demand? A specific forecast from your development comes here in terms of cumulative annual growth rate in the automotive market related to silicon carbide, and according to their figures, the US market only will be growing from $420 million in 2018 up to 1.9, almost $2 billion in 2024. Another piece of information comes from Cree, now Wolfspeed, in terms of their production capacity. On this chart shows what the normalized production capacity is forecast in the coming 4 years, and you can see that they according to their forecast, they expect a growth by a factor of 5.5 compared to year 2020. Question is, when it comes to automotive applications, basically there is a strong demand for reliability. If you look at this very simple table, you can immediately figure out that automotive applications seldom require less than 15 years continuous operation, more often up to 20 years. And this means that silicon carbide, among all, should be able to make it. But unfortunately, so far, we have no data about this. So one of the biggest challenges in transitioning to silicon carbide is figuring out how much, reliable such kind of technology can be, and how long lifetime expectation can be. No doubt, silicon carbide presents many benefits in once. So there is a large improvement in thermal conductivity, which increases the heat dissipation. There is a larger, of course, band gap from the name wide band gap, which increases basically several parameters, among them the capacity of blocking voltage at higher temperatures, higher breakdown field, which is another very nice feature because better improves the trade-off between on-state resistance and blocking voltage, higher dielectric constant, which is not necessarily a benefit, but it's not that higher actually. It's comparable to previous technology. So I mean, not big in this, not big deal in this. And then a higher saturation velocity, which increases significantly the switching speed. Point is, what about reliability? So what are the challenges we have to face when it comes to adopting silicon carbide in applications which traditionally have been made by using silicon traditional technology? So let's move to the core of this speech. I would say a rough classification of current challenges in silicon carbide MOSFETs reliability are among packaging issues, semiconductor issues, and short circuit issues. So by packaging issues, I mean something which is related to the packaging itself. So in this case, for example, we have a typical bond wire liftoff, which turns out to be very critical in silicon carbide applications. By semiconductor issues, I mean something which is affecting the semiconductor itself, typically with a parametric drift or something like this. And finally, by short circuit issues, I'm referring to something which is happening in connection with short circuit events, like in this picture here, where I show a post-failure analysis result after a short circuit test evidencing a crack through the gate structure. All right, let's move to the first one a little bit more into detail. So packaging issues in silicon carbide MOSFETs. So packaging related issues, I would say, are basically arising because of a intrinsic smaller per ampere area. And this comes from the fact that thermal conductivity is better than silicon, and power dissipation capacity is better than silicon. But together with this, there are two challenges. One of them is that you have basically a smaller chip for the same current to manage, and this means that you have simply lesser area for landing bond wires. And this turns into a higher per bond wire current, which I will show you in a slide, is very challenging phenomenon. And the second is that because of the lower thermal resistance intrinsic of the material, which is good, of course the thermal constants, time constants are smaller, or thermal transients are faster, and basically with the same stimulus, with the same electrical stimulus, you have a larger temperature swing. In this picture here, you can see a detail of a single chip or a multi-chip module produced by Rome. And you can see that because of the limited area, only 2 bond wires are possible to be put on the chip top on the source side. This is, by the way, a 36 ampere chip, so this means that the current per bond wire is up to 18 amperes. Some experimental results point out how critical this current density through bond wires could be. So in this slide, you can see some experiments which have been conducted at Aalborg University, where we simultaneously cycled components under power cycling and measure the temperature swing through optical fibers here. And in this table here, you can see the maximum temperature, junction temperature, minimum junction temperature, and temperature swing, and period, cycling period for 2 experiments, for 2 conditions, condition 1, condition 2, which only differ in the drain current. The way we obtain this is to use a different gate voltage for the 2 cases, in such a way for the higher current we got a lower on-state voltage, and all the way around for the other. So in order in such a way to keep constant the power dissipation. Well, a detail of the inside of the module under test is depicted here on the top right hand side of this slide, and some experimental results are shown here. As you can see here, what we obtained is a obvious difference in the behavior of the 24 amperes compared to the 18 amperes. Everything else was the same, so this difference in behavior can only be related to the higher current density through the bond wires, which, as I mentioned before, is a rather critical parameter when it comes to reduced area silicon carbide chips. All right, the second challenge, in my opinion, is a semiconductor level. What happens? Basically, this experimental setup shows you a little bit what the phenomenon looks like. In this case, we use the commercial silicon carbide MOSFET module, and we measured separately the voltage drop across bond wires and the voltage drop across the semiconductor. This is possible because we use the power cycling, which is intrinsically made under low voltage conditions, so no need for high voltage isolation. We could use the intermediate connection, which is called the Kelvin source, which is very typical of silicon carbide MOSFET and MOSFET modules, because this way the gate driver is better performing in terms of EMI and also in terms of reduced stray elements of the gate loop. Again, we measure the the junction temperature through fibers, optical fibers is in the picture here, and here you can see some results during power cycling. Now the interesting thing is that you can see in the beginning of power cycling, at pristine condition, the on-state voltage drop was looking like this. So you can see the blue curve here, but after power cycling, after the entire the end of life, basically the on-state voltage drop was increased up to the red curve. The bond wire voltage drop was also increased, but we were able to to discriminate what the difference was between the semiconductor alone and the bond wire alone. And you can see the results in this picture, where the semiconductor voltage drop is the red one and the bond wire voltage drop is the blue one. There is a slight increase in the bond wire, some ups and downs, but obviously the semiconductor voltage is a definite and I would say very remarkable increase, around, I would say, 10%, as pointed out in this picture. Temperature, junction temperature was also drifting up with the time, which means that basically this is not just a measurement error, but as a matter of fact, higher voltage means higher power at the same current, which is forced from the outside, and this ends up in higher temperature swing, as you can see from this picture, where the initial temperature swing is the bottom curve, the blue one, and then the green and the two red ones on the top. What happens? What happens is relatively well known. It is called a charge trapping mechanism. Basically, if we focus on this picture here, where you can see a schematic cross-section of an elementary cell of a MOSFET, in this case a silicon carbide MOSFET, what happens is that at extreme conditions, for example, high junction temperature and the high current density, it may happen, there is a non-zero probability that a hot electron finds its way towards a gate electrode, which is positively charged, and along this way can remain trapped inside the gate oxide. This possibility is very likely to happen is a lot more likely to happen in silicon carbide rather than silicon, because it is a wide bandgap semiconductor, and manufacturers, to hold the threshold voltage to reasonably low value, they have to fabricate the gate oxide with a reduced thickness compared to the silicon counterparts. Well, when this happens, you have two concurrent phenomena happening at the same time. One is gate leakage current. So your gate driver is charged actually with active power, and charge trapping. This charge trapping can last minutes, hours, or even days. And in this case, you're adding up additional negative charge to the gate voltage, which ends up in basically increasing the threshold voltage. Now, if you just look at this equation, which is the very basic equation of on-state voltage drop of MOSFETs, well, if you increase the threshold voltage, of course, this number at the denominator decreases. But being at the denominator, the on-state voltage drop increases in turn. So this means that because of this drifting phenomenon, the on-state voltage drop increases, and this increases, of course, the power dissipation at a given current level. So schematically, what happens during power cycling is that, being constant the temperature swing, the average and the maximum temperature drift up, as in this case, and of course the power losses in this top figure here, in the schematic top figure here, increase as well. All right. And the last challenge, in my opinion, is a short circuit. Short circuit withstanding capacity is largely demanded in nowadays applications for safety reasons. You have to go through at least one short circuit in the semiconductor life without killing it, and being able to give time to the protection circuits to intervene and stop everything and put everything on the safe side. And this is even more true in application like automotive, which are, I would say, safety critical. Well, no doubt short circuit is a very stressful condition, and we have to bear in mind that high temperature coming from it both alter threshold voltage and packaging. So the risk is that in the case of silicon carbide, short circuit is a lot more challenging than in IGBT case, because the transconductance of the components themselves is a lot higher than IGBT counterpart, and I personally have been observed short circuit currents in the range of a factor of 10 or even higher compared to the nominal current, which is definitely not the case for traditional silicon, where you get a factor of 4 or 5 or something like this. In this case, again, you can see a commercial module which has been rated at 1.2 kilovolts at 20 amperes, which has been tested against short circuit, just to figure out how the characteristics stay stable after one or more short circuit events. The principle we used here is to use a power cycling, which is a clear indication of how fast the component is degrading. And then we stopped power cycling. We used short circuit stress, which can be one event, two events, a number of events, and then keep doing power cycling. Of course, this sequence is compared with a sequence where there is no short circuit stress in the middle, and in the end we could compare what the effect of short circuit stress is. There's a picture here where you can see a typical sequence of short circuit events. This is the gate side and this is the drain side, both voltage and current together. Some results here in this picture and this slide. You can see that this is the power cycling temperature before and after short circuit. The blue one is a zero number of cycles, and the red and the orange one, orange and the yellow ones are the power cycling temperature right before and right after the short circuit. In this case, it's 50 repetitions of short circuit, just to emphasize what the effect was. But later on, we did it also with a very limited number of repetitions, 1 or 2, and then 60 and 100K. And you can see that suddenly, right after the short circuit event, there is a significant jump in temperature swing between the orange one and the yellow one. This voltage drop, this effect has an immediate consequence also on the voltage drop here, where you can see in this diagram the difference between the non-short circuited and the short circuit sample, which in the beginning were absolutely superimposed before short circuit event, and after it there is a significant difference in the on-state voltage drop. And this schematic picture here, you can see that because of short circuit, a very sound conclusion is that there is a sudden increase in the on-state voltage drop, which is affecting all the rest of the component life, which is, as I mentioned before, a very big challenge, because this means that silicon carbide apparently can withstand, silicon carbide MOSFETs at least, apparently can withstand short circuit for one or more events, but as a matter of fact, right away there is a degradation of the on-state characteristics. This takes me to the end of this speech, so I'll be drawing some prospects and summarizing key concepts discussed in this talk. So first of all, some prospects I would like to emphasize. Well, there are some challenges. First of all, is cost. There is no doubt that cost is still a limiting factor. It's very difficult to adopt silicon carbide at the moment because the semiconductor itself is more expensive, and economies should come from the rest of the topology of the converter. So which means that the approach to a cheaper design should be, I would say, a little bit more at the overall design level rather than a semiconductor level. And the second thing is that operating temperature. Well, what I've been pointing out before is that such effects like packaging degradation and semiconductor degradation are heavily temperature dependent. So basically, we do not observe such kind of effects below 150, or I would say even higher temperature. So this means that at the moment, maximum operating temperature is a limiting factor. And in my opinion, this is also limiting the possibility of increasing power density and efficiency thanks to silicon carbide. Because on the one hand, you can use a lot higher power density, but on the other, you have to limit the maximum junction temperature. So it's not clear to me what the benefit is of transitioning to silicon carbide, as far as the operating temperature is limited at 150 or 175. We do need better interconnections. I've been pointing out how packaging can be severely affecting the overall silicon carbide reliability. There are many possibilities, new concepts. Of course, silver sintering is an option about the solder layer. Copper bond wire is another option. But something is, in my opinion, is largely demanded to enable the final adoption on silicon carbide. It is also worth to point out that scenario is very dynamic. I believe I've been mentioning that Wolfspeed is predicting a large increase in their fabrication capacity. They have been, among other things, invested $1 billion in a new wafer fab, which promises to be some 30 times bigger as before in terms of capacity. And also companies are working hard for enlarging and making at affordable price new interconnections component concepts like, for example, copper wire bonding. All right, to summarize my speech, I would like to give you some bullet points. So first of all, it is clear that the electric vehicle market is booming. There is a 120 million vehicle forecast by 2030, basically by the end of this decade, which is quite a remarkable number. Most of them are, private vehicles or low load commercial vehicles. The automotive sector is no doubt will be driving the power electronics development in the present decade. This has been pointed out by several surveys and market forecasts. And from my point of view, there are three main challenges in terms of reliability of silicon carbide MOSFETs: package-related issues, semiconductor-related issues, and short-circuit-related issues. Prospects for faster adoption of silicon carbide, just discussed in the last slide, are lower cost, higher stable operating temperature, new interconnections, and new investments in terms of both of semiconductor fabrication and interconnection fabrication. This concludes my talk. Thank you very much for your attention. My reference email is here for your convenience. Thank you very much.